We will use the coin toss example to do the approximation to normal distribution and see how well does the normal distribution approximates the binomial distribution. So let's see, we are looking at the case of 100 coin toss. We will use the binomial distribution function to compute the probabilities for different outcomes from 0 heads to 100 heads is equal to binom of this number of success 100, number of trials 100, and the probability of success is 0.5 in every trial, and we don't want this to be cumulative, and we calculate the probability, which is a very minuscule small little probability, almost zero. I double click this to fill all the values. We'll see the maximum probability somewhere in between at 50 heads, which is 0.0795. Now what we can do is we know that the expected value of a normal distribution function is NP. Let's also calculate the Q also, which is nothing but 1 minus P is equal to 1 minus P. And we know the standard deviation of X is square root of NPQ. So we can compute it is equal to N multiplied by P, and this one is square root of N multiplied by P multiplied by Q. Now for approximating the binomial distribution as normal, we need to verify two conditions. NP should be greater than equal to 5 and NQ should also be greater than equal to 5. So let's see if those conditions are met. Is equal to N times P and N times Q. Since both the values are greater than equal to 5, we can approximate it as a normal distribution. We can compute the normal distribution function values at different values of X, but those are not the probabilities. They may appear to be probabilities, but they are not, because in continuous distribution the probability at a given value of X is 0. We always calculate the probability between two values. So let's calculate the normal distribution function. X is 100, given the mean 50 and standard deviation of 5, and we will calculate the probability mass function, which is 0, false. Alright, so we get this value, which is very small little minuscule value as 0, but this is not the probability. But just for the sake of comparison, we're calculating it so that you know you don't need to calculate those values. We expect this value to be very close or the highest at the value 50 heads. This is 0.07958 and this is 0.07978. But this is still not the probability values, because this applies only for continuous functions, and this is only the function value of the function normal distribution, but these are not the probabilities. So the way we apply the probabilities is by using the continuity correction, And how do we apply the continuity correction? So we'll find the area around plus minus 0.5 of 100 to be the probability at value 100. So we will calculate is equal to norm of this 100 plus 0.5 with the mean of 50, standard deviation of 5, and we will calculate the cumulative value. Minus, we will subtract the norm dist at 100 minus 0.5 comma 50 comma 5 comma cumulative. This is the value that we use to calculate the probability of x is equal to 100 using the continuity correction. I can go ahead and fill this value across all the cells. We'll see this is probably because of the resolution of x. It's not able to detect these small little differences. But again, if you look at 50, we should be able to see the true value using the continuity correction. So continuity correction value is pretty close to the binomial distribution values. So 0.07958, 0.07965. So that's the correct value. Now let us look at these values and where this difference is coming from. By just doing a plot of this, so let's do a line plot. We'll kind of change it. So let's kind of maximize the area that it can capture. Now point is, this is spurious because this is 100 to 0, which is not the right thing to plot here. We see all three of them are here, bx, nx, and c of x. Now the x values, will fix it. So we want the x values to go from 100 to 0. So we can see now this is representing the two values on x. Now let us change it to a combo chart and see what we get to see here. So let's see, manage the template. No. Let's fix each of them. Chart type. Now b of x, that's the orange color thing, that's a bar. N of x is the normal, c of x is this. So let's kind of undo it first and then change the option. Right click, to column. So we get this. Okay, this is the incorrect one. We don't want this to be, we rather want this one, orange, b of x to be that way. So this will be line. So now what you are seeing here is, this is the binomial function, and let me give normal a change of color make it, maybe let's say make it red. So we are not able to see it because it's hidden under it. So let's go and change the thickness of this line. Make it 6. So we can see that this line is here. Yellow line is the continuity correction. And let's kind of represent this gap by maybe just 5%. 5% is too less, make it 10%. So now what you're able to see is, let me zoom it. So the difference that you're seeing is the height of the bar is your binomial probability, and the yellow line, the gray line, which is the thickest line, which is the normal distribution function, but the continuity correction applied probabilities are represented by these yellow lines. So you see this yellow line is slicing over this binomial probability. So some part is left over and some extra part is captured, because continuity correction is the area under the curve between this point and this point sliced off here. So that's what is creating the difference in those values, and this is the correct way of computing the probabilities by applying the continuity correction. Right? So we are able to see the coin toss. These orange bars are nothing but the binomial distribution of x. The n of x is shown by that thick gray color line, and the continuity correction based values, which is calculating the area under the curve, which you can kind of consider the thickness of the bar multiplied by the height sliced off in this fashion, is your continuity correction values.